So we're looking at deriving the energy stored in a capacitor. So the basic idea is that a capacitor is a simple setup wherein we have charges that are accumulated on two plates. So obviously these charges will push each other. Given opportunity, they will flow. When they flow, they are able to do some work, and so they have energy. They have the potential to do some energy. So that is a funda, and that's what we are trying to figure out. How much energy can it, how much energy does it have? How much work can it do? So how do we calculate? See, the question of how do we calculate is, if you understand this, the derivation is very simple. It's just 2-3 liner. But why is that we are doing it is very important. That awareness is what we want. Okay, out of the syllabus, it's not about, okay, this is the topic and this is the formula. It's not supposed to be that. Please, it should make sense to you what we are talking about. It's not complicated, but listen to me. This has to be very clear. So, how do we calculate it? See, initially the capacitors have no voltage between them because there are no charges, right? Because there are no charges implies there is no voltage. And so there is no electrical field between the plates. Now, say there is a charge. An equal charge will appear at the other end, and we have an electrical field. So, how do we do calculate energy of anything till now? In ninth grade, we calculate the potential energy by doing work. Here too, we are using the same funda. We are using the concept of work. So we can imagine doing work ourselves by transferring electrons from one plate to the other one by one. So we can think of an electron, right? Pick it up and drop it over here. So we can keep doing that and look at what amount of work we have to do. So intermediate, along the way, we'll have a voltage which is not equal to 0, right? So is it as simple as counting the number of electrons, moving from one end to the other end? Just multiply force into displacement, all of that. Well, it is force into displacement in some sense, but it's not totally so. What I mean is, it's not as simple as a single value of force into displacement. Well, the complication is over here. As the charge builds, so does the electric field between the plates, right? So we had a positive charge and a negative charge on these plates. So what do? They build an electrical field, right? Starting from the positive to the negative. So what happens then? Like how we had derived bringing in 3 electrons or 3 charges from infinity, the work that we need to do and all of that, right? Go back to that derivation. We are connecting that over here. So we are making use of, we're using the topic work needed to get 3 charges, right? So we are making use of that. Here too, as and when you get each of these electrons from the negative end to the positive end, we come across a electrical field which keeps on adding, which keeps on building. As a charge builds, so does the electrical field. So say for the second electron, this is the electrical field. But once this comes off, what happens? That pair creates an electrical field of its own. Next electron that we have to get from the negative to positive end, that has to encounter 2 of them, right? Similar to your derivation on this over this topic. So as and when this happen, as and when we have n number of charges that has come out, so the difficulty will increase by n factor, difficulty level, right? So we will have various work for every charge we move. So basically, each time we move a charge, the amount of work will not be constant. It's not a simple multiplication and addition. But we know we have a tool. What is that? Yes, we'll make use of first the smallest work and then add all them up, add them all using Correct. Integration. Does it make sense? Then let's start with your derivation. So this is how we calculate. Okay, guys. The actual derivation starts over here. So initially we have 0 as there is no charges, right? And there's no electrical field. So along the way we have non-zero voltage. So basically we have charges, right, on the inner plate actually. So we're considering a capacitor with capacitance C. Initially the capacitor has no charge on its plates and the potential difference across them is 0. Very simple statement. Next, to transfer a small amount of charge dq from one plate to other, no work is initially required, right? Very first charge, a small charge dq will have no objection, right? Because there's no electrical field over here. So aram it will go from one end to another end. Again, go back to that topic. So this, all of these points will make sense. However, as charge accumulates on the plates like this, a potential difference develops, right? Which is incremental. This potential difference creates an electrical field between the plates which opposes the transfer of additional charges, right? So we can think of a charge dq being transferred from negative to positive plate, or you can think of a charge plus dq transferred from positive to negative. Again, it's just imaginary. Physically, we're not doing that. Suppose that q is the charge on the capacitor, right? At some moment of time, like intermediate level. So this is the charge q, and here minus q. At some instance during the charging process, the work needed to transfer a charge of dq from negative to positive, okay, negative to positive, from negative to positive plate is given by what? Well, we know that it will be equal to voltage at that intermediate level into dq. So where we have this voltage to be equal to the charge at that instant of time divided by the capacitance of capacitor, right? Right, guys? Okay, so we can further substitute it and we get a new expression. We'll do it over there. So as an idea, it would be something like this, right? Initially the potential will be 0. As and when the charge increases, the potential increases. It's a simple relationship. V and Q are directly proportional. So say we have a charge dq over here. We're transferring a small charge dq, right? So this is a small charge dq. Now the work needed to transfer dq is the area work needed transfer dq will be equal to the area of this particular rectangle, right? Then this area will give us what? Yes, work till now. Work that has been done till now. Is it not, guys? As per this formula, V into Q, right? Potential difference into charge will give us what? Right, work done, is it not? So basically this is length into breadth in some sense. Since it's a triangle, it's half into base into height if you guys want to think of it. But if not, if you guys are very strong with your 11th grade syllabus, I'm sure you will be able to understand. So here it's very clear that this length into breadth, that's what gives us the work. So basically, in total, if you are moving a charge of 0 till q, the total work will be the sum of all the work that is being done in transfer of charge from 0 to capital Q. And from here we have 0 to Q, dW will be QC, Q by C into dQ. As you can see, it's a very simple expression. C is a constant, so I'll take it out. Integration of Q is Q square by 2, and this is 0 to Q, right? So basically, when you substitute this, it will be, let me write it in a neat manner. That's it, as simple as that, right? Of course, when you substitute Q and all of that, substituting Q is equal to CV. So what do you end up with? Then the energy, the work. So this is all potential energy, is it not? So the energy will be equal to, so we have CV square by 2. That's one more expression. Okay, what else can we have? C into V is Q, so QV by 2. That's one more expression. Yeah, I think that's good enough. Does it make sense? So only complicated stuff over here is this part. You need to be able to understand why we are integrating, not just adding up. This gives you a concrete idea of integration and the concept of when to use integration. That's more important to me than the final answer. Okay, guys. So if you understand this particular, derivation, this particular video and discussion, which you should have seen by now. If not, you're not doing the right thing. Now you can pause and have a look.